Hello, today we're going to talk about our class project on an embedded system for violent crime detection and analysis via captioning using multimodal audio-video fusion. And I'm Milton Kumar Kundu, and my project partner was Kazim Mahi, and we both are going to present this work today. So this is the outline of our presentation. So the problem statement. We aim to actually automatically detect violent and non-violent events in video clips using multimodal information and notify the authority through this captioning. The motivation is to support real-time safety monitoring, reduce manual review workload, and improve response times. So our system takes raw MP4 videos as input, and the output is a predicted violent, non-violent video segment. So if it is a violent video, dense caption is generated and shared with the authorities. So why this problem actually matters? Manual video monitoring is very slow and inconsistent, and violence often appears subtle, brief, and partially occluded, requiring models to integrate multiple cues. So if we have a robust automated system, it can provide safety, reduce human workload, and enable deployment on edge devices like Raspberry Pi 5. So we faced a few technical challenges in our work, like multimodal fusion, temporal reasoning, class imbalance, deployment constraints, dense captioning, and information sharing. So in some previous works, like in number 1, a multimodal framework was proposed that decomposes violent detection into recognizing specific subconcepts, for example, fights, explosion, gunshots, etc., using separate neural network for visual and audio features, and then fuses these features through a dedicated fusion network to identify violent scenes. So this paper actually solves the multimodal fusion part. In 2, the authors developed a multimodal neural network with attention using temporal information, fusion, and mutual learning modules to improve violence detection in videos by effectively combining visual and audio features. In number 3, authors fed the video and audio feature fusion to a classifier which used short and long-term dependencies to classify the violent videos. Their model handled the class imbalance problem very efficiently. So in this work, we have used this XD violence dataset compiled from 91 movies and in the wild YouTube videos. It contains diverse scenarios like movies, cartoons, sports, games, etc. And it also contains videos from CCTV, handheld cameras, and car driving recorders.
For caption generation, we also use the XD violence dataset, but the dataset does not contain any ground truth textual annotation. So we use the pre-trained bimodal transformer to generate the initial caption and skim through that to ensure that there is no garbage captions. For feature extraction, we use X3D Access and EMNet as the previous feature extractor i3D and BGGish are unsuitable for embedded deployment.
For multimodal input collection, we used cameras to collect video information and microphones to collect audio information. And then both streams are segmented into aligned 30-second windows, so audio and video correspond to the same event. We used X3D XS for video feature extraction and EMNet for audio feature extraction. And we used RGB features, optical flow features, and audio features to classify our data. For variable length handling, we used a custom collate function that pads RGB flow and audio sequences to the max length in the batch. We also used temporal masking to ensure that the model only learns from the real data, not parity 0. For feature projection and fusion, each modality was projected to a shared 128-dimensional space via linear layers and ReLU, then concatenated into a fused representation. We also use temporal modeling with graphical convolutional networks. We use 3 GCN layers to capture temporal relationships. We also used identity adjacency matrix with residual connections and ReLU. We also used the masked temporal pooling to show that only valid time steps contribute to the pooled 384-dimensional video embedding. Then for the final classifier, we use 2-layer MLP, and it is trained with cross entropy loss, and best checkpoints are saved by validation accuracy. We used the quantization-aware training, unstructured pruning, and post-training quantization to reduce the model size. We only applied the fake quantization to projection and classifier layers, not the GCN layers, due to its sensitivity to quantization.
For caption generation, we use the bimodal transformer architecture. So the bimodal transformer consists of 2 parts, a caption generator and a proposal generator. We do not use the proposal generator. The caption generator consists of an encoder that gets the video feature and audio feature. They are self-attendant, and then they are bimodally attendant, so we get a video attended audio feature and audio attended video feature. In our model we used only one layer, but in the original work there were two encoder layers. For the decoders, it gets output from the previous encoders, that are audio attended video and video attended audio, and also the previous caption embeddings. So the embedding is self-attended, then it is bimodally attended with the audio attended video and video attended audio. They are concatenated and pass through a fully connected layer, and this generator generates the probability distribution over the vocabulary. So this is our whole system. This is the microphone, this is the Raspberry Pi 5, and this is the 5 megapixel camera.
This table shows the comparison between full, pruned, and pruned plus quantized models. So full and quantized model have almost the similar size, but pruned and quantized model is much smaller than the other models. But all the models have almost similar average precision and almost similar ROC AUC. This two figure shows the ROC AUC curve and the precision recall curve for the pruned and quantized model. And this table shows the comparison with existing methods on the XD-valent dataset. And we can see that our model has the highest average precision than any other model working with this XD-valence dataset.
This is the performance of the original model without any quantization and pruning on the validation dataset. As you can see, blue 3, blue 4, and meteor are increasing. This is the performance of the prune model on the validation dataset. As you can see, there is some performance decrease in the middle, but the performance is increasing and thereafter. And this is the performance of full model, prune model, and pruned and quantized model. As you can see, they have comparable meteor blue 3 and blue 4. This is the performance in terms of model size and inference latency. The pruned and quantized model has a significant less size than the full model and the prune model, but greater inference latency. The inference latency is in minute because it is on the whole validation dataset. The validation dataset contains video with a total duration greater than 30 minutes. These are the papers we have used in our work. Thank you very much for watching the presentation.